Hi everyone, I'm Kun Wang from the University of Texas in Dallas. Today I will present various hints. Sorry. Design thermal glove through thermal and tactile integration for watch object manipulation. Is that okay? Or I can hold it. Okay. This work was done in collaboration with Yasser Sinha, Dr. Henjie Gill, and Professor Jin Yang King. Thermal feedback will largely enhance our experience in VR. In virtual environments, we mainly use our hand to do interactions with virtual objects, and we expect it to experience normal thermal interactions such as touching a hard surface, grabbing a cup of coffee, filling the food liquid, and grabbing a chestnut. A thermal glove will be an ideal interface for all those scenarios, and it's an exciting area of growth in wearable technology. However, fabricating a thermal glove faces a lot of challenges in many aspects. First, the obstruction. When we place the thermal actuators and the fingers and palms, it will make it extremely hard to do the grasping and other hand manipulations. Also, because of the more peltiers heaters we use, we need other peripheral attachments such as coolers and circuits to drive the system, which make it a large, hard, complicated for the whole system. And if I want to provide the whole thermal feedback cover the entire palm and the finger, a large number of thermal actuators will need to be used, which makes it pretty hard to scale systems if you want to change this to other body parts as well. Because of the large number of thermal actuators we use, it makes the power consumptions way more higher, and which hinders the feasibility of fabricating a thermal glove. So, how can we solve those issues? We utilize the vibration-induced thermal referral to tackle those issues. When we activate one thermal actuator and one tactile actuator simultaneously, actually we perceive the thermal sensation and the location of the tactile actuators. Which means, through this approach, we can detach the thermal actuators and target area. Instead, place on tiny tactile actuators and area and deliver the thermal sensation. And with this approach, we can expand the number of tactile actuators and create various thermal patterns by using just one thermal actuators. We can create a localized thermal pattern, a line, and even like a full global thermal sensations by different tactile modulations. Through this, we can solve the problem of obstructions because we minimize the size of the actuators from the bulky thermal actuator to the tiny tactile actuator. And completely, since we use very limited numbers of thermal actuators. And also scalability, we can easily expand our system to various body parts by expanding with different numbers of tactile actuators. And also power consumptions, since tactile actuators just consumes way less powers than the thermal actuators. We conducted 3 real studies to validate and evaluate our approach. First study, we focus on the placement. The goal is to find the optimal placement of thermal actuators, which can deliver the localized thermal feedback. Here shows our setup for the fingers. We place the thermal actuators in the middle of the phalanx, and both ventral, which is inner, and dorsal, which is the outer side of the finger. Those locations are peripheral locations, which will not hinder our hand movement. And we place the tactile actuators in the middle of phalanges and other parts. For each trial, participants will experience the stimuli with the tactile and thermal and corresponding fingers. After experiencing the stimuli, they need to answer whether they perceive the thermal sensation and the tactile location, and then draw the perceived area on the tablet. Through this, we can get the results of the occurrence rates of the thermal referral and also the heat map of the perceived thermal sensation. Here shows the result. The occurrence rates of the thermal sensation on both sides are pretty high, exceeding 80%, which is suggesting we can successfully deliver the thermal sensations and the ventral side by placing the actuators and the dorsal side. And also, the perceived thermal area shows high alignment with the locations of tactile actuators, which is shown as the purple dots in this heat map. It indicates we can achieve the localized thermal feedback as well. For palm conditions, we tested two positions. One is at the ventral side of the palm, another is at the back of hands on the dorsal side. We still use the same criteria for selecting those locations, which will not hinder our free hand movement. We use 9 Weber tactile actuators, which are arranged in a 3x3 arrays put on the palm, which cover the whole area, and also maintain a high number of combinations in thermal pattern rendering. We follow the same procedures as in the finger conditions, and the result shows a substantial discrepancies in the occurrence rates between the two sides. And for the perceived thermal areas, it covers the locations of tactile actuators, and also has high dispersed to the location of thermal actuators. So in this study, we found the high occurrence rates of thermal referral can be achieved on both sides of the fingers and on the ventral side of the palm. The perceived thermal distribution is generally larger than the size of the tactile actuators. And for finger, it's more aligned with the location of tactile actuators, and for palm, it will be more dispersed to the location of the thermal actuators. Based on the studies, we finalized our placements for actuators, which is the actuator will be placed on the finger and the dorsal side, and the palm and the ventral side. Next, we conducted another studies focused on the thermal patterns. We wanted to know how various thermal patterns were perceived with the proposed actuator placement. Here shows the finger patterns. It contains both localized and global patterns with an increase of complexity from single actuator, double, and triple on one finger, and also complex patterns which cover all 5 fingers. We follow similar procedures as in previous studies, where the thermal and tactile stimuli will be delivered simultaneously. For each trial, participants will need to draw the perceived thermal area on tablet. Here shows the result. So for the single patterns, the perceived thermal area will be more concentrated at the location of the tactile actuators. With the increase of the complexity, the perceived thermal area will be more focused at the middle phalanx, and a unified thermal perception will be observed with the complex patterns. Here shows the patterns for the palms. We designed several patterns with increase of the complexity. For single pattern, consists of a line. With cluster, consists of 4 or 6 groups of tactile actuators. And complex patterns with increase of the complicated shapes. And for combined patterns, we include both fingers and palm. The result shows for simple and cluster patterns, the distributions of the thermal sensation will be more aligned if the tactile actuators is placed more closer to the actuators. With complex patterns, a full hand thermal coverage is achieved, and in combined patterns, we observed a unified thermal sensation. In this study, we find with the increase of the tactile actuators, we can achieve a unified perceived thermal area. And the full finger coverage can be achieved with 2 or 3 tactile actuators. And for finger conditions, the perceived thermal area will be more clustered in the middle phalanx. And for palms, we observed the perceived thermal area will be more aligned if the tactile actuators is more closer to the actuators. We present fairy hands, a pair of wearable gloves which strategically equips the thermal and tactile actuators to create the thermal sensations through thermal and tactile integration. Fairy hands leverage the insights from our previous studies, delivering various thermal effects, then dynamically varying in both spatial and temporal dimensions. Then, we evaluate how fairy hands influence the user experience in immersive virtual environments. We implemented 2 distinct things. First thing is match variable, which we assess more on the thermal patterns. Participants can manipulate with merge objects by transferring from one hand to another, and control the size of the object by grasping and stretching their fingers. The size will be changed, and the perceived thermal sensations will be synced with the visual cue. For another thing, we focus more on the localized sensations, where participants will need to wash their hands using the water flow. They can perceive the localized thermal sensations and the location where the flow flowing to their fingers and palm. We conducted an open-ended questions interviews to get more insights about the experience. Overall, participants were highly enthusiastic about both rare things, facing the immersive and realistic experience they encountered. They can clearly perceive the distinguishable thermal sensation, including the localized, the pattern, and the global. And interestingly, some participants also perceived the wetness illusions through the thermal and tactile integration. Also, they appreciate the sameness manipulations, where the high congruency of tactile and visual is delivered. They love the multisensory feedback, which largely enhance their experience and lead them to give high immersion and realistic readings, and also high level of enjoyment. In this paper, we propose a unique approach which renders the thermal illusion through strategically placed thermal actuators. With this approach, we can minimize the obstructions of the virtual object manipulation, render various patterns in both spatial and temporal dimensions. With insight from that, we fabricated the thermal glove, fairy hands, which will largely reduce the complexity and energy consumptions in thermal glove design, which gave participants an immersive and realistic experience. That's all. Thank you so much for your listening, and I'm glad to take any questions.
If you have any questions, feel free to come to the center.
Thank you. Thank you for very wonderful presentation. I'm Kosuke Shimizu from University of Tsukuba. I do have a question on the tactile sensation to fingers. You know, intuitively, when 3 or 4 fingers are stimulated, the fingertips seem to feel the haptic thermal focus point. You know, but your research, result is like this. You know, middle of the fingers. You know, this. I'm just curious why this has happened. Yeah, that's it.
Yeah, thank you so much for your questions, and that's like very important insights. So for that things, we got assume it's going to be a sort of one phenomenon called phantom tactile illusions, which means if we like activate 2 tactile actuators simultaneously and with the same intensities, we actually can perceive phantom tactile illusions at the center of that. So since we just place the tactile actuators and all the middle of phalanx, and this phantom tactile illusions will also like induce one phantom tactile stimuli in the center, which will enhance like the perceptions and that point. That's why when we activate all 3, participants actually can also perceive the sensations more clustered in the center.
Thank you. Can I have one more question?
Yeah, of course.
Does users' perception of finger or palms will change if users' hand shape, hand form is changes?
Yeah, that's a very good point. So as also like one issues when designing like all those thermal gloves, since we want to do the virtual object manipulations, and it's very important to make sure like the tactile actuators like tightly attached to the surface to deliver sensation clearly. So for that, we in our thermal gloves, when we do experiments, we put the Velcro straps to tightly attach them on the finger. And I'm not sure if you tried the demos. So in our like fabricated thermal gloves, we also have like the Velcro straps and each phalanx to make sure the actuators is tightly attached to your fingers to deliver a clear stimuli.
Okay.
Yep.
Thank you very much.
Thank you.
Any question? Okay, if not, we'll move on to the next thought, and let's thank Hao Kun again.
Thank you.